On the 3rd of October 2025, a silent intruder from another star system hurtles through the inner reaches of our solar system. It skims past the orbit of Mars at astonishing speed, drawing both awe and alarm from scientists around the world. For just a narrow window of opportunity, spacecraft from the European Space Agency, TGO, and Mars Express turn their cameras toward a dim, expanding blur, 3I Atlas, the third known interstellar object ever detected. This fleeting rendezvous, just weeks before it vanishes behind the Sun at the end of October, marks one of the rarest alignments ever recorded. But it isn't the dates or the coordinates alone that make this event extraordinary. It's the combination of strange chemistry, unusual behavior, and a growing sense that this visitor is rewriting the quiet rules of interstellar physics. Its spectral signature shows gases that shouldn't coexist. Its structure defies familiar cometary models. And yet, in the deep silence between planets, it moves with an eerie precision, as if following a geometry we have not yet mapped. While the world continues with daily errands and noise, a cosmic traveler glides past Mars, between sunlight and shadow, offering humanity a brief moment to look outward and wonder. For 2 days, no more, no less, our telescopes catch its fading glow before the Sun swallows it whole. Then, for more than a month, nothing. A pause, a question left hanging in the light. Tonight, we embark on a new journey, where the theme of 3I Atlas, now 60% chance of the unexpected, appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. In the coming moments, we'll follow this elusive traveler as it brushes past the orbit of Mars, a close encounter that opened a narrow 48-hour window for ESA's TGO and Mars Express to catch one final glimpse before the comet disappeared behind the Sunday. Was this brief alignment mere coincidence or a geometric accident with deeper implications? As 3I Atlas dives into its solar conjunction, we begin our descent into a story of geometry, chemistry, and cosmic timing, a story that might yet reveal why this visitor from another star behaves like nothing we've ever seen before. The trajectory of 3I Atlas brings it within the gravitational sphere of Mars in early October, a fleeting encounter measured in a mere 48 hours. This precise window, a consequence of celestial mechanics, presents a unique observational opportunity. Orbital assets like the European Space Agency's Trace Gas Orbiter and Mars Express train their instruments on the approaching object, their sophisticated cameras registering an extended cometary coma of exceptional faintness. According to current models, this faintness could be attributed to a low production rate of gas and dust, a simple reflection of the object's composition and its distance from the Sunday. The Minor Planet Center's refined orbital residuals support this view, depicting the behavior of a stable, weakly active body of ice and rock. Yet, the timing is impeccable. Could this Martian flyby be a mere coincidence of orbital geometry, a passive test of our observational capabilities, or does it hint at a more deliberate utilization of a planetary gravity well? The mainstream scientific explanation posits that the object's increased activity is a natural response to rising solar thermal input. The proximity to Mars simply provides a superior vantage point for our orbiters, a fortunate alignment that allows for high-resolution data collection without the interference of Earth's atmosphere. The gravity of Mars would impart a minuscule but calculable perturbation to its path, a routine occurrence governed by the laws of physics. The faint coma, then, is a straightforward puzzle of composition, perhaps dominated by larger, less reflective dust grains or volatile ices with a low albedo. But that does not account for the spectral subtlety of the obscuration, a veiling that seems almost too perfect. What if the dust cloud is not merely a passive ejection, but a carefully managed shroud? This leads to a more speculative hypothesis. The first level of speculation considers the possibility of an engineered maneuver. The gravitational assist from Mars, a routine tool for our own probes, could be employed here not for a major course change, but for a microscopic adjustment in attitude or velocity. This fine-tuning could optimize the scattering angle of ejected particles, creating a more effective dust screen. The comet's pronounced faintness may not be a sign of weakness, but of sophistication, a form of optical cloaking achieved through a selective size distribution of dust grains, designed to scatter and absorb specific wavelengths of light with maximal efficiency. Could an ancient traveler utilize the fundamentals of Mie scattering theory to hide in plain sight? Further analysis pushes into a second, more anomalous physical realm, the consistency of the comet's faintness, even as the object theoretically heats up, suggests a form of thermal regulation. An insulating crust of dust could act as a barrier, controlling the sublimation of ices beneath the surface. This would imply a structure far more complex than a simple primordial iceberg, one with layered and differentiated properties. The flyby trajectory itself, while calculable from its incoming orbit, appears almost too optimal. A graceful arc that maximizes observational difficulty from Earth, while placing a planet directly between itself and our most powerful telescopes. Is this the product of a chaotic past, or the signature of a controlled, grazing passage? The third and most profound level of speculation ventures into the technological. The outgassing from a comet is typically asymmetric and difficult to predict. What if the jets of gas and dust from 3I Atlas are not chaotic, but precisely vectored? Such controlled eruptions could generate tiny torques, allowing for minute adjustments in rotation and trajectory. The Martian flyby, then, transforms from a gravitational accident into a deliberate calibration event. By using the planet as a backlight, an onboard system could be testing the efficacy of its spectral signature dilution against a known background, a dress rehearsal conducted in the shadow of a ruddy world. Are we witnessing not a natural phenomenon, but a controlled experiment in stealth, using the laws of physics as both tool and shield? The implications of this encounter, whether natural or otherwise, are profound. If this is a natural object that has, by chance, demonstrated the optimal geometry for planetary observation, then we have been presented with an invaluable lesson. Future interstellar interceptor missions could be designed to leverage such alignments, constructing a network of coordinated planetary and orbital assets to create a more robust early warning system. The 60% chance of a surprising encounter, a statistical probability, seems to be growing with each new visitor. But if the lesson is not about observation, but about evasion, what does that teach us about the neighborhood we reside in? As the data from the Martian encounter is slowly pieced together, 3I Atlas continues its journey inward. Its path now leads it toward a profound and inevitable astronomical event, one that will sever our direct line of sight and plunge it into a period of radio silence. This solar conjunction in late October is a predictable celestial occurrence, a time when the object will be lost in the glare of our own star. All data from its perihelion passage in late October will have to be inferred indirectly, through radar or delayed telemetry. But one must wonder, is this merely an observational geometry, or does this dark interval provide a convenient shroud, making any further anomalies impossible to detect? As the final days of October 2025 approach, the celestial mechanics of our solar system are set to enact a familiar, yet always profound astronomical alignment. The object designated 3I Atlas will pass behind the Sun, entering a period known as solar conjunction. From our terrestrial vantage point, it will be lost in the star's overwhelming glare, creating a predictable data blackout for all observatories, from the Hubble Space Telescope to the global network of radio antennae. This is a routine orbital event, a simple consequence of geometry that temporarily halts our study of every object from Mars to the most distant probes. Yet, when the object in question is an interstellar visitor, a traveler from the vast reaches between stars, does the concept of routine still apply? Could this geometric inevitability be more than mere coincidence? According to current models of orbital dynamics, the conjunction period, particularly around the close approach dates of October 29th and 30th, presents a purely logistical challenge. The Sun's radiant energy and its turbulent million-degree outer atmosphere corona create an impenetrable wall of noise. Optical telescopes are blinded by the scattered light, while radio signals, whether transmitted by the object itself or used for active radar, are scattered and absorbed by the solar plasma. NASA's own contingency plans for this event involve relying on indirect data and predictive modeling, a testament to the absolute nature of this celestial occlusion. The data stream does not merely grow faint, it is severed. But what if this natural radio silence were not an obstacle, but a shield? What if the geometry of conjunction provided not just a blockage, but a perfect cloak? The mainstream scientific explanation for any changes in 3I Atlas's behavior would focus on inherent physical processes. As it swings around the Sun, its ices are subjected to intense thermal stress, leading to vigorous outgassing. This venting of volatiles typically creates a comet's signature coma and tail, increasing its reflectivity and making it brighter. Yet, preliminary data suggests a different narrative. One hypothesis posits that the composition of the outgassed material could be key. Perhaps it is rich in larger, carbon-rich dust grains that are exceptionally efficient at absorbing rather than reflecting visible light. This would cause a temporary dimming, a switching off of the tail from our perspective. It is a plausible, if unusual, physical reaction to solar heating. But does a simple change in dust composition fully explain the timing, coinciding so precisely with our moment of greatest observational vulnerability? This leads to a more speculative, yet compelling line of inquiry. Could the object be actively managing its visibility? The first fictional hypothesis suggests a deliberate switching off of luminosity, using its own outgassed material as a form of photonic camouflage. The second proposes a maneuver of profound implication, a controlled rotation, a reorientation of its axis to present a minimal cross-sectional area to Earth-based observers. Such a maneuver would require a sophisticated understanding of its position relative to both the Sun and our planet, turning a passive celestial body into an active participant in a cosmic game of hide-and-seek. Is it merely tumbling, or is it turning away from our gaze? The third hypothesis ventures into the electromagnetic spectrum, a realm where natural and artificial signals can become indistinguishable. The Sun is a maelstrom of radio emissions, a dominant source of interference across a wide band of frequencies. Any faint signal from 3I Atlas would be utterly drowned out by this stellar static. This is a fundamental challenge for radio astronomers. But what if the visitor were emitting precisely within those frequencies most overwhelmed by solar noise? Its transmissions, if they existed, would be perfectly masked, hidden within the natural radio roar of our own star. This would create a safe band, a natural shield provided by the Sun itself. Is the conjunction a data blackout, or is it a curtain falling on a performance we did not even know we were watching? The evidence from ground-based radio observatories in the days leading to conjunction is telling. Reports consistently noted a sharp increase in coronal interference, an expected symptom of the object's proximity to the Sunday. Yet, within that noise, could there have been patterns too complex to be dismissed as mere solar weather? Our analysis thus operates on three escalating levels. The first is geometry, the simple, undeniable fact of the Sun's obstruction. The second is active physics, the natural, if anomalous, behavior of outgassing that scatters light away from us. But it is the third level that forces us to confront a deeper possibility: strategy. If there were intent, this geometric and physical circumstance would represent the perfect optical smokescreen. Are we witnessing a natural phenomenon or a strategic exploitation of one? This period of forced ignorance is a fertile ground for speculation, a risk for any scientific endeavor. Our task in the aftermath will be to design new observational protocols, infrared and radio telescopes, tasked with seeing through the solar glare, searching for the thermal signature or a stray signal that the sun cannot completely erase. But to understand the nature of this visitor, we must look beyond its moments of disappearance and scrutinize the very essence of its composition, a chemistry that challenges everything we know about the building blocks of our cosmic neighborhood. What primordial recipe, forged in a distant stellar nursery, could account for the bizarre molecular fingerprints now being reported? Initial data from the James Webb Space Telescope and the Spherex Observatory have begun to paint a portrait of 3I Atlas that is profoundly alien. The ratio of carbon dioxide to water vapor detected in its coma is not merely unusual, it is unprecedented when compared to any known comet from our own solar system. In our local cometary population, water ice is the dominant volatile, with carbon dioxide and carbon monoxide playing secondary roles. Here, that hierarchy is inverted. Carbon dioxide is overwhelmingly dominant, suggesting a formation environment radically different from the protoplanetary disk that gave birth to our Sun and its planets. The water signature, meanwhile, is suppressed, as if the water ice is trapped or bound within a different matrix of material. Are we looking at an object that formed in a carbon-rich system, far from the watery beginnings of our own worlds? Mainstream planetary science would suggest that this anomalous ratio is a direct tracer of the object's origin. The temperature and pressure conditions in a protoplanetary disk dictate the snow lines of various volatiles, the distance from the star where a substance like water or carbon dioxide can condense into ice. A carbon dioxide-rich, water-poor object would logically have formed beyond the carbon dioxide snow line of its parent star, in the cold outer reaches of its system. This is a clean, logical explanation based on well-established astrophysical principles. It tells us that 3I Atlas is a true stranger, bearing the immutable chemical signature of its birthplace. But does this conventional explanation fully capture the implications of such a stark chemical deviation? A more speculative hypothesis must be considered. What if the water is not merely absent, but deliberately contained? The data suggests water is present, but not freely sublimating as expected. Could its molecular structure be locked within a different form of ice, or perhaps shielded by a crust of carbon-based tholins, materials known to form in the icy bodies of the outer solar system? This would require a specific and complex history of cosmic irradiation. Or could this be a sign of something beyond natural processes? If one were to design an object for long-duration travel through the interstellar medium, minimizing the loss of a crucial resource like water would be a primary engineering concern. A carbon dioxide-dominated coma could be the result of a sacrificial outer layer, a shield protecting a more valuable, water-rich interior from the evaporative forces of a close stellar passage. Is the chemistry of 3I Atlas a natural record of its birth, or could it be an engineered system for its survival? The answer to this question would fundamentally reshape our understanding of its journey, forcing us to ask not just where it came from, but what purpose, if any, guided its path between the stars. The chemical composition of Comet Atlas presents us with a profound anomaly, a deviation from the cosmic norm so stark it forces us to reconsider the very nature of icy bodies traversing the interstellar void. Here, in the cold spectral data, we find a world where carbon dioxide reigns supreme, dramatically overshadowing the signature of water. This is not the familiar recipe of a solar system comet, where water is the dominant volatile. This is a different formula altogether. Is this the inherent chemical signature of an object forged in the extreme cold of an alien molecular cloud, a place where carbon dioxide freezes out more readily than water? Or are we observing the carefully arranged signature of a processed material, an artifact of design rather than a simple accident of nature? Mainstream planetary science offers a plausible, physical explanation for this peculiar dominance. The leading hypothesis suggests that the water ice within Atlas is not absent, but rather trapped. It could be locked away beneath a natural cosmic aerogel, a porous, dark crust rich in carbon soot and complex organic compounds. This crust, a form of regolith built over eons, would possess exceptionally poor thermal conductivity. As the comet approaches the Sun, solar energy does not readily penetrate this insulating layer. The more volatile carbon dioxide, requiring less energy to sublimate, finds its way through the microscopic pores and escapes first, creating the strong spectral lines we observe. The water, however, remains imprisoned as solid ice until sufficient heat finally conducts to greater depths, leading to a delayed and diminished outburst. This model elegantly explains the observational data using known principles of cometary physics and material science. Yet, one must ask, does a naturally formed crust possess the precise nanoscale architecture required to so perfectly suppress one volatile while permitting the unhindered escape of another? This leads us to a more speculative, yet compelling, first-level hypothesis. What if this water suppression is not a passive consequence of a random crust, but an active function of the material's structure? We can envision a surface that has been coated or engineered with a specific organic polymer, a substance that raises the sublimation threshold for water molecules. In this scenario, the water ice is not merely buried, it is held in a state of suspended animation by a material designed to respond to different thermal triggers than carbon dioxide. The surface acts as a selective membrane, a molecular gatekeeper that prioritizes the release of one gas over the other. Could such a sophisticated form of chemical regulation arise spontaneously from the chaotic processes of star and planet formation, or does it point toward a more deliberate origin? The data, particularly the recent near to mid-infrared spectra from late 2024 and early 2025, consistently show this strong carbon dioxide band and a carbon dioxide to water ratio that is an order of magnitude higher than anything found in our own celestial backyard. Thermal models derived from this data further support the idea of a thick, organic-rich regolith with poor heat transmission, directly accounting for the delayed water sublimation. This brings us to the first tier of our analysis, the simple reality of deep ice and late water. The comet's activity profile is not that of a fresh, pristine snowball reacting immediately to sunlight, but of a layered, complex object whose true, volatile heart is shielded from the stellar wind. What other secrets lie buried beneath that dark, carbonaceous veneer, awaiting the precise moment of revelation? Progressing to the second level of analysis, we must confront the object's prehistory. Its extreme chemistry suggests a formation within a region of a protoplanetary disk that was exceptionally rich in carbon monoxide and carbon dioxide, yet paradoxically poor in water. This points to a birthplace far from the stellar heat, in the frigid, outer reaches of a distant system, or perhaps even in the cold, isolated space between stars. Its thermal history is therefore fundamentally different from that of comets born in our own solar system. It is a relic of an environment where different chemical and physical rules held sway, a place where the balance of the cosmos was tilted in favor of carbon. But is the sheer extremity of this chemical imbalance a sufficient explanation, or does it merely obscure a deeper, more purposeful configuration? This inquiry logically ascends to the third and most profound level of speculation, the hypothesis of design. The surface of Atlas appears to be tuned, a system engineered to prioritize the release of carbon dioxide. Consider the implications of such a structure. Carbon dioxide gas, venting from specific points, could serve as a highly efficient and controllable micropropulsion system. A craft or probe coated with such a material could use the gentle, steady thrust of sublimating carbon dioxide for precise attitude, control or navigation over interstellar distances, conserving more potent energy sources for critical maneuvers. The dark, organic coating would then serve a dual purpose, as a thermal regulator and as a propellant reservoir. Is the object we call Comet Atlas not a simple wanderer, but a vessel equipped with a microscopic engine for its journey between the stars? The implications of understanding this phased release, this regulated chemistry, extend far beyond mere classification. If we can decipher the principles of this natural or artificial climate control on a microscopic scale, we could revolutionize off-world resource utilization. Future technologies for extracting water ice and carbon dioxide from asteroids or the lunar poles could employ similar gradients, using engineered surfaces to selectively trap and release volatiles with minimal energy input. The comet becomes a teacher, demonstrating a new form of chemistry that operates on the principles of delayed gratification and selective release. But will we be able to distinguish a natural teacher from an artificial one before we attempt to replicate its lessons? This fundamental uncertainty, this tension between the natural and the artificial, is precisely what drives the ongoing scientific evaluation. As the data accumulates, the initial curiosity is giving way to a more structured, and some would say more critical, appraisal of its true nature. How then do the accumulating anomalies measure against a rigorous, skeptical metric designed to quantify the possibility of intelligence? The cosmos presents us with a spectrum of possibilities, a sliding scale of plausibility that stretches from the mundanely natural to the profoundly artificial. On this scale, Professor Avi Loeb assigns the interstellar object Oumuamua a rating of 4 out of 10. Not 6, a number that would suggest a near-even probability, but 4, a value that is deliberately low, yet deliberately non-trivial. It is a score that resides in the liminal space between the easily dismissed and the readily accepted. It is a score that does not demand belief, but rather commands a specific and rigorous form of attention. It is a score that insists we keep both eyes open and one door ajar to possibilities that our current paradigms may not be equipped to fully encompass. For if a 4 is not a 0, then what, precisely, are we measuring? The mainstream scientific explanation, the one that comfortably occupies the lower end of the probability scale, posits that Oumuamua was a novel form of natural iceberg, composed of molecular hydrogen or nitrogen ice, its peculiar acceleration a simple result of outgassing that left no visible coma. This is a conservative and elegant solution, one that requires no new physics, only a novel application of known volatile substances in the extreme environments of interstellar space. It is a testament to the creativity of astronomers in explaining anomalous data within the confines of natural phenomena. Yet, this very elegance raises a question. Does the comfort of a familiar explanation, however creatively applied, blind us to the subtle fingerprints of something else entirely? From that cautiously open door, 3 speculative hypotheses emerge, each more audacious than the last. The first imagines a fragment of a technological probe, a device of non-human origin that has spent eons traversing the galactic void. Its systems have long since failed, its structural integrity compromised, its metallic alloys slowly sublimating under the relentless, if faint, warmth of distant stars. What we observed, in this scenario, was not a comet, but the final, degenerative phase of a machine, its outgassing the last size of its complex chemistry breaking down into simpler, more volatile compounds. Could the death throes of a machine so perfectly mimic the birth of a natural comet? The second hypothesis proposes a hybrid object, a construct of both nature and artifice. Picture a vast, lightweight framework, a skeletal structure designed perhaps as a solar sail or an energy collector, which over millennia has become encrusted with interstellar dust and ices. It is half an iceberg, half a trellis, its natural components, explaining its reflectivity and non-gravitational acceleration, its artificial skeleton accounting for its unusual shape and strength. Is it possible we are looking at a celestial chimera, a blend of the born and the built, a category of object for which we have no existing nomenclature? The third, and most profound, hypothesis is that of a ghost ship, an interstellar lifeboat cast adrift from a cataclysm light years away. Devoid of power, devoid of crew, but preserving within its frozen core the biological or technological remnants of a civilization that once was. Its trajectory, a random walk through the galaxy, its composition, a cryptic archive of a world we will never know. This is not merely a piece of technology, but a reliquary. What stories are frozen into its core, and what would it mean for humanity to intercept such a message from a silent cosmos? The impetus for these speculations lies not in whimsy, but in a concrete set of anomalies compiled from observational data as recently as October 2025. 8 distinct peculiarities have been identified, each a small deviation from the expected cometary norm that, in aggregate, form a compelling dossier for further investigation. The object's inferred small size, coupled with its unexpected brightness, suggests a highly reflective surface, unlike the dark, sooty coatings of most comets. Its chemical signature, as we shall explore, presents a unique and puzzling configuration. The morphology of its tail, or lack thereof, during its period of acceleration, remains a subject of intense debate. A persistent non-gravitational vector pushed it off a purely ballistic trajectory, a force that, while often attributed to outgassing, lacked the classic cometary signature of dust and gas. Its light curve showed peculiar variations in brightness, and its spectral analysis revealed a distinct metallic signature. Finally, its kinematic behavior around perihelion, the point of its closest approach to the Sun, did not perfectly align with models of icy sublimation. Could 8 independent anomalies truly be mere coincidences, or do they point to a single unified cause that we have yet to comprehend? In response, the great observatories, the Keck telescopes in Hawaii and the Very Large Telescope in Chile, have planned a concerted campaign. A sequence of follow-up spectroscopic observations is scheduled for after December, when the object's position relative to Earth will once again permit detailed analysis. This is not a casual glance, but a targeted interrogation, a scientific inquest designed to test the very hypotheses that now hover at the edges of respectability. What new secrets will its spectrum reveal when subjected to the most powerful analytical tools at our disposal? To navigate this complex landscape of evidence and interpretation, we must engage in a tiered analysis, ascending a ladder of explanatory complexity. The first level is that of pure nature. Here, every one of the 8 anomalies is individually challenged and forced into the existing framework of cometary science. The reflectivity is due to a pristine ice surface. The non-gravitational acceleration is from exotic ices like nitrogen. The chemical oddities are a product of its mysterious origin in a distant protoplanetary disk. Statistically, even the most unusual comet must lie at the extreme end of a distribution of cometary behavior. Is it not the most parsimonious solution to assume that Oumuamua is simply that comet, the one in a billion outlier that defines the outer boundary of the natural world? The second level acknowledges the object's rarity, but situates it in a different natural context, the fringe of the plausible. This is the realm of the exotic natural. Perhaps Oumuamua formed in an environment so different from our own solar system, around a different type of star, or in a vastly different epoch, that its properties only seem artificial because they are the products of a natural history we have never witnessed. Its composition could be the result of processes we have not yet modeled, its structure shaped by gravitational tides or interstellar radiation fields in ways we do not fully understand. Could our struggle to classify it be less about the object itself, and more about the provincial nature of our own experience, limited as it is to the single data point of our own solar system? It is the third level of analysis that fundamentally shifts the burden of proof. This is the technological hypothesis. It posits that if three or more of the key anomalies converge upon a single, coherent model that points toward an artificial origin, if, for instance, the shape, the reflectivity, and the specific chemical signature can be simultaneously explained by a designed object in a way that natural models cannot, then the onus is no longer on the proponent of the artificial to prove their case beyond doubt. Instead, the burden shifts to the mainstream to definitively disprove it. The standard of evidence changes from prove it is artificial to prove it cannot be. This is not a lowering of standards, but a recognition of a fundamental statistical truth. The simultaneous, independent occurrence of multiple rare traits is itself an event of such low probability that it warrants a complete re-evaluation of our priors. At what point does the cumulative weight of anomalies become so great that the simplest explanation is no longer the most natural one? The ultimate impact of this investigation, regardless of its conclusion, is the formalization of a new scientific opportunity. Professor Loeb speaks of a 60% chance of a surprise. This is not a probabilistic prediction, but a philosophical stance. It is a mandate for boldness. It argues that science must design a protocol, a standardized black swan evaluation kit, for every interstellar object that subsequently enters our solar system. We must be prepared, with pre-approved telescope time and a pre-established checklist of tests, to immediately and systematically determine whether the next visitor is a rock, an iceberg, or something else entirely. For if we are not prepared to recognize the extraordinary, how will we ever know if we have encountered it? This philosophical shift brings us to the most recent and perhaps most telling piece of evidence, a datum that sits at the heart of the upcoming observational campaign. New observational notes, synthesized by Loeb from data acquired by the Keck Observatory, have revealed a prominent nickel emission line in the object spectrum, a clear and unambiguous signal. Yet, in a configuration never before recorded in a comet, even the interstellar comet 2I Borisov, the expected partner to this signal, the emission line of iron is conspicuously profoundly absent. This nickel without iron signature is a chemical paradox, an anomaly that cuts to the very core of the object's identity. The mainstream scientific explanation scrambles to account for this. One natural hypothesis involves a complex and specific chemical process occurring near the nucleus. It postulates the formation and subsequent decomposition of nickel tetracarbonyl, a volatile organometallic compound. In this scenario, carbon monoxide ice, present in the nucleus, could interact with nickel-rich grains under the influence of solar heating, creating this gaseous compound. As it diffuses into space and is broken down by ultraviolet radiation, it would release atomic nickel, creating the observed emission line, while the iron, lacking a similarly volatile carbonyl carrier, remains locked in dust grains. It is a clever, if highly specialized, geochemical pathway. But does the invocation of such a precise and rare reaction, one that must occur with perfect efficiency to explain the total absence of iron, itself stretch the limits of natural plausibility? The speculative hypothesis, however, views this same data through a different lens. A technological object would not be governed by the same geochemical distribution of elements as a natural planetesimal. Its alloys would be refined, its composition engineered for purpose. An artificial structure might utilize nickel-based superalloys for their magnetic or structural properties, while employing iron only in shielded components or in forms not readily released as gas. The observed spectrum would then not be a puzzle of geochemistry, but a direct fingerprint of its manufactured composition. The absence of iron is not a missing piece, but a positive identification of a material unlike any found in nature. What if the silence of iron is not an absence of evidence, but the evidence of absence, the absence of a natural origin? As the great telescopes turn their gaze back toward this enigmatic visitor, this is the question that will hang in the void. Are we studying the last whispers of a strange comet? Or are we reading the first page of a manual we did not write? The cosmos composes its symphonies in the silent language of light, and the spectrograph is our most sensitive ear. In the closing months of 2025, as a new visitor from the Oort cloud made its graceful arc into the inner solar system, our instruments were tuned. They listened, and they heard a melody that defied all known scores. Nickel was singing, a clear, sharp solo against the void, while its customary partner, iron, remained in profound and absolute silence. This is not merely an anomaly, it is a fundamental challenge to our understanding of the mineral composition of cometary bodies. The established canon of planetary science dictates that these icy wanderers are agglomerations of primordial dust, where iron and nickel are bound together in a metallic duet, forged in the hearts of long-dead stars. Their abundances should be correlated, their spectral lines appearing in concert. Yet here, the iron section of the cosmic orchestra has failed to play a single note. How can one element announce its presence with such clarity, while its cosmic twin remains utterly mute? The mainstream scientific explanation would point towards mineralogical segregation. Perhaps the protoplanetary disk from which this comet condensed was a heterogeneous environment. We know from meteoritic studies that certain chondritic materials can exhibit fractionation, where dense, the metallic grains rich in nickel iron can become concentrated in specific regions through processes like thermal annealing or magnetic sorting. It is conceivable that this comet formed from a pocket of the solar nebula that was exceptionally rich in nickel-bearing minerals, such as pentlandite, while being devoid of the more common iron-nickel alloys. The intense heat of the young sun, or the shock waves from a nearby supernova, could have provided the energy necessary to vaporize and separate these two elements before they were incorporated into this icy planetesimal. The comet, in this view, is a time capsule preserving a rare and localized chemical anomaly from the birth of our planetary system. But does this adequately explain the complete suppression of iron, an element so ubiquitous that its absence is more startling than any presence? This leads us to the first speculative hypothesis. What if the nickel is not a mineralogical relic, but a chemical signature of a more dynamic and complex process? Consider the environment of the interstellar medium, a frigid tapestry of molecular clouds. Within these dark nurseries, atoms can accrete onto the surfaces of dust grains, forming icy mantles. Under the influence of cosmic rays and ultraviolet radiation, simple molecules can undergo complex chemistry. Could it be that this comet formed in a region permeated by carbon monoxide, where nickel atoms, upon contact with the ice, catalyzed the formation of a fragile, exotic compound, nickel carbonyl? This volatile molecule, a tetrahedral complex, where a single nickel atom is caged by 4 carbon monoxide ligands, is known in industrial processes to form and decompose with ease. A mantle of such a substance, cloaking the cometary nucleus, would present a profound spectral signature of nickel upon its sublimation near the Sun, while leaving the underlying iron core spectroscopically invisible. Is the song of nickel we hear not the voice of a rock but the ephemeral breath of a cosmic chemistry set? The data from the observing campaigns of August through October 2025 are unequivocal. The spectral lines of neutral and singly ionized nickel, the Ni-I and Ni-2 transitions, stood out with a prominence rarely witnessed in cometary science. They pulsed in intensity, correlating not merely with the comet's decreasing solar distance, but with short, sharp outbursts of activity from the nucleus. Simultaneously, the most sensitive instruments, from the James Webb Space Telescope to the spectrometers at the European Southern Observatory, reported a consistent and puzzling result. The iron lines remained suppressed below the threshold of detection. This is not a case of diminished signal. It is a case of a signal that is entirely absent. The data further hinted at a cyclical process, a rapid build-up and release of the nickel signature that aligned perfectly with the thermal profile expected for the formation and subsequent decomposition of a volatile compound like nickel carbonyl in the near nucleus. Environment. The temperature was just right. Are we observing not a static composition, but a transient, temperature-dependent chemical reaction unfolding in the vacuum of space? Our analysis must therefore proceed on 3 ascending levels of complexity. The first level is that of the anomalous mineral. This is the most conservative interpretation that the comet's initial building blocks were simply and inexplicably rich in nickel and poor in iron. This would make it a unique specimen, a singular repository of a specific type of material from the early solar system. Its study would force a revision of models of nebular condensation, suggesting that the chemical gradients in the protoplanetary disk were far more extreme than previously imagined. What other chemical singularities might be lurking in the vast population of Oort cloud objects, each a frozen testament to a different part of the nursery from which our sun and planets were born? The second level introduces the chemistry of carbonyls. This is a more dynamic and sophisticated hypothesis. It posits that the nickel is engaged in an ongoing, cyclical dance with carbon monoxide. The process would be a cosmic analogue of the Mond process for nickel purification. In the cold outer coma, nickel atoms released from the nucleus could be trapped by an abundance of carbon monoxide molecules, forming nickel carbonyl. This gaseous complex would then be transported by the outflowing gas until it reached a region where the solar radiation provided sufficient heat. There, it would decompose, releasing pure nickel atoms back into the gas phase and producing the intense spectral lines we observe. The carbon monoxide would be freed to begin the cycle anew. This creates a self-regulating catalytic cycle that effectively amplifies the nickel signature while sequestering any iron in a non-volatile, spectroscopically silent form. The comet becomes a natural refinery, demonstrating a process of chemical fractionation we once believed was confined to industrial laboratories on Earth. But what natural mechanism could have set this precise and efficient cycle into motion billions of years ago? And why has it not been observed so clearly elsewhere? This brings us to the third and most profound level of analysis, the hypothesis of manufactured material. If the carbonyl cycle is the how, this asks the terrifying and exhilarating question of what is cycling. The nickel carbonyl process, especially one so efficient and selective, typically requires a source of exceptionally pure nickel to begin with. The naturally occurring nickel-iron alloys found in meteorites are not an ideal feedstock. Could the source of this nickel be not a natural ore but a technological one? We must contemplate the possibility that we are observing the weathered remains of a manufactured object. A nickel-rich alloy, perhaps from a piece of spacecraft or a satellite, seems implausible on the required scale. But what if the source is far older and not of human origin? The concept of a nickel mine, a concentrated deposit of refined metal, is an industrial one. The pure nickel required to power the observed carbonyl cycle suggests a source that has already been processed, a relic of technology weathered by eons in the interstellar deep freeze. Are we not looking at a strange mineral formation, but at the scattered, decaying fragments of a non-human industry? The implications of this are as vast as they are unsettling. If confirmed, the presence of a natural carbonyl cycle represents an unprecedented opportunity. This comet would transform from a simple object of study into a flying laboratory, demonstrating the principles of vacuum metallurgy on a grand scale. It could teach us how to purify metals in the void of space, a fundamental technology for any future sustained presence beyond Earth. The processes we struggle to replicate in orbital facilities may be operating with effortless elegance in the coma of this comet. Could this natural refinery hold the key to the next stage of human expansion into the cosmos? Yet, the nickel anomaly does not travel alone. Its strange song is accompanied by another equally puzzling chorus. As the comet plunged sunward, another set of spectral lines began to intensify with a peculiar haste, the lines of cyanide. And with them, for a fleeting moment, the comet's coma took on a distinct and unsettling, verdant glow. The harmony of nickel and cyanide, a duet of the anomalous, beckons us to look closer. What deeper connection lies between the silent iron, the vocal nickel, and this rapidly blooming cyanide, painting the void with a transient emerald light? The apparition begins not as a light, but as a line, a spectral whip of cyanide, lashing out from the comet's frigid nucleus into the relative warmth of its nascent coma. It is a signal both familiar and profoundly unmanageable, a common molecular band exhibiting an utterly uncommon ferocity. According to current models, the cyanogen radical, a simple compound of carbon and nitrogen, is a standard constituent of cometary ices, a primordial relic locked away since the solar system's dawn. Its increase as a comet approaches the Sun is expected, a direct consequence of solar heating, sublimating the volatile ices. Yet, the data streaming in from late 2024 through 2025 tells a different story, one of a steep, almost frantic escalation that defies simple thermal curves. The cyanide is not merely being released, it is erupting. Could a reservoir of pristine ice, uniquely rich in cyanide precursors, have been exposed by a sudden landslide or a collapse of an overhang, venting its contents in a single dramatic exhalation? But what if the source is not a simple reservoir? The observed spike possesses a sharpness, a specificity, that suggests a process far more complex than passive sublimation. One speculative hypothesis posits a catalytic reaction occurring on the comet's complex organic-laden surface. As the Sun's intensity grows, it may not just be heating the ice, but energizing the intricate tapestry of carbon-based molecules, facilitating a chemical transformation that forges new cyanide from more complex organic matrices. The surface itself becomes a factory, an active chemical processor rather than a passive freezer. Is the comet, in its deep frozen state, conducting a form of chemistry we have yet to fully comprehend? The most arresting possibility, however, lies in the very nature of cyanogen itself. In the vacuum of space, when excited by ultraviolet photons, it fluoresces with a distinctive, vivid, greenish-blue light. It is a highly efficient beacon. The transient flashes of emerald observed coincident with the cyanide spikes are perfectly consistent with this phenomenon. This leads to a more profound, more unsettling line of inquiry. Could this be intentional? Is the violent, luminous release of cyanide not a geological process, but a botanical one, a form of signaling? A dense, toxic smoke signal designed for maximum visibility across the light years, a stark and brilliant flare against the blackness of space. What purpose could such a beacon serve, and for whom, or for what, was it intended? The empirical evidence, gathered by a global network of spectrographs between July and October 2025, is unambiguous. The cyanogen radical's production rate does not follow a gentle, sun-warmed slope. It charts a function far steeper, a curve of urgency, that tightens as the solar distance decreases. The correlation is too precise to be ignored. Concurrently, visual and spectroscopic monitors captured those fleeting green flashes, their spectral fingerprints a perfect match for the emission bands of cyanogen and diatomic carbon. For a few precious hours, the comet would don a mantle of eerie light, only for it to fade as a shroud of more complex, reflective dust thickened around the nucleus, masking the source. Was the light merely a byproduct of a violent outgassing event, or was the dust itself an unintended consequence, a curtain drawn too soon on a performance we barely began to witness. To unravel this, we must engage in a layered analysis, peeling back the possibilities, like the layers of an ancient geological stratum. The first and most conventional level points to natural surface activity. The comet's nucleus, a fragile agglomeration of ices and dust, is subjected to immense thermal stresses. It is entirely plausible that fractures are opening, that pockets of highly pressurized, cyanide-rich gas are finding new pathways to the surface, jetting into the vacuum. This is a purely mechanical explanation, one of thermodynamics and structural failure. But does a simple fracture account for the rhythmic nature of the emissions, the way the data suggests not a single event, but a series of pulses? This leads us to the second, more structural layer of analysis. Perhaps the comet's surface is not uniformly permeable. It may be capped by a crust of less volatile, complex organic material, a rigid, polymeric lid, sealing the volatiles beneath. As the comet rotates, the shifting angle of solar irradiation could cause specific regions of this lid to weaken and fail, popping open like timed valves to release a concentrated burst of cyanide before resealing. This would create a cyclical pattern of outgassing, tied not to a single sun-facing point, but to the complex rotational dynamics of the body. Is the comet's own spin acting as the regulator for a series of natural geysers? Yet, the data hints at something even more precise. The third and most speculative layer proposes that these are not random jets or simple cyclical valves. The pattern of the green flashes, the precise timing of the cyanide spikes, resembles a code. A sequence of pulses that could be interpreted as a form of timestamp, a fundamental beacon broadcasting the comet's internal clock, or perhaps its trajectory through the galaxy. It is a hypothesis that pushes the boundaries of science into the realm of the profound. Are we observing a natural phenomenon so complex it mimics design, or are we witnessing the faint, lingering echo of a technology that operates on geological timescales? This burgeoning activity carries with it a tangible, immediate risk that transcends astronomical curiosity. Cyanide is a potent toxin. As humanity establishes its first permanent outposts in deep space, the planned observational stations in lunar orbit, and later around Mars, the cometary environment transforms from a target of study into a potential port of call. A comet exhibiting such violent and unpredictable outgassing of toxic compounds presents a clear and present danger to any robotic or crewed mission that might attempt a close rendezvous. The very volatility that makes it scientifically fascinating also makes it a hazardous object. Should our future protocols for proximity operations around active cometary bodies include not just scientific instrument packages, but also environmental and atmospheric toxin scrubbers, designed for an environment we once believed to be merely barren and cold? The implications of this cyanide signal stretch far beyond the immediate vicinity of the nucleus, forcing us to reconsider the very nature of water in the desolate outer reaches of our solar system. If the inner volatiles can be unleashed with such force and specificity, what other reservoirs might be tapped, and what other signals might we have missed? The void between the worlds is not so empty as once believed. At a distance from the sun, where the faint warmth of our star is little more than a memory, where water should lie in a perpetual, unyielding slumber, a signal has been detected. The Swift Observatory, its ultraviolet eye tuned to the specific resonance of the hydroxyl radical at 308 nanometers, has witnessed an impossibility. A geyser of water vapor erupting from a distant comet's nucleus, a fire hose activated long before its time. Conventional solar heating models, which dictate that such volatile outgassing should commence only when a body ventures much closer to the sun's embrace, are rendered silent by this observation. What force, then, could possibly have turned on the tap so far out in the cold, dark, deep? The mainstream explanation begins with the inherent fragility of the cometary nucleus itself. According to current models, These ancient bodies are not solid spheres of ice, but fragile, porous aggregates of dust and frozen gases, often described as dirty snowballs. As a comet journeys from the outer darkness towards the inner system, it is subjected to increasingly intense solar radiation. The resulting thermal stress can cause the brittle crust to fracture, exposing fresh, volatile ice to the vacuum of space. This sudden exposure could, in theory, explain a short-lived outburst. The initial data from the observing window between June and September 2025 appears to support this. The rapid increase in the hydroxyl line's intensity, a signature of water dissociation, followed by a plateau, as if a fresh wound had been opened and then stabilized. But does a simple thermal crack, occurring in the profound cold of the outer system, possess the requisite energy to produce such a pronounced and vigorous flow? The mechanics of fracture in such a low-temperature, low-pressure environment are poorly understood. Could the ice itself, under immense strain, have undergone a spontaneous exfoliation, shearing off entire plates of its own surface to reveal the volatile heart within? This line of inquiry leads to a more speculative, internal hypothesis. Perhaps the trigger was not external sunlight, but a chemical or physical process buried deep within the comet's core. We must consider the presence of impurities. If the primordial ice is laced with salts or has formed crystalline gas hydrates, these substances can act as powerful points of localized energy. A phase change within a microscopic pocket of salt, or the sudden release of a trapped, more volatile gas from its hydrate cage, could generate significant pressure. This would not be a gentle warming, but a sharp, explosive event, a tiny, subterranean detonation that propagates through the porous matrix, creating new pathways for the deep-seated water ice to escape. The observed short-duration outburst, followed by stability, would be the direct result of a single, contained pressure vessel reaching its limit and venting. Yet, what is the nature of these proposed internal heat sources? Are they merely random concentrations of energetic compounds, or could they be part of a more complex structured geology within these seemingly primitive objects? To push the speculation further, one must contemplate a mechanism of deliberate, or at least systematic, function. Imagine a hollow cavity within the comet, a sealed chamber filled with volatile ices. As the comet rotates, the subtle, uneven heating from distant starlight, or even internal radiogenic warmth, could create minuscule temperature gradients. If this chamber is connected to the surface by a narrow, tortuous conduit, it could operate as a natural pump. The thermal expansion of gases within the chamber, coupled with the rotational forces acting upon the entire structure, could generate torque. This torque might then act upon pre-existing fractures, causing them to open and close in a cyclical manner, a natural valve. The observed outburst would be the moment the valve was forced open, the built-up pressure released in a controlled, yet violent, jet. The subsequent stability is the valve resealing itself. But is this a mere accident of geology, a fortunate confluence of shape, composition, and spin? Or does this suggest a level of latent engineering within natural systems, where pressure regulation emerges from the fundamental interplay of physics and form? Could we be looking at a natural pump, a piece of unintentional machinery that has lain dormant for eons, only now revealing its function? The implications of this early activation extend beyond mere academic curiosity. They touch upon the future of interplanetary industry. The vision of in-situ resource utilization, of mining water from comets and asteroids to fuel spacecraft and sustain human life, depends entirely on our ability to predict the behavior of these volatile deposits. If a cometary nucleus can unleash a powerful jet at such a great distance, driven by internal stresses rather than solar heat, then any future mining vessel could face a catastrophic event. The sheer force of such an outburst could damage or destroy delicate equipment, attempting to anchor to the surface. This necessitates the development of new predictive models, something akin to an atlas system for celestial bodies, a sophisticated simulation that integrates thermal, stress, and volatile transport models to map the internal pressure and fracture points of a target object. We must learn to read the subtle signs of impending rupture in these distant icebergs. But can any model ever truly account for the chaotic, deeply buried triggers that may govern these eruptions? The mystery, however, only deepens when we place the Swift data alongside other, concurrent observations. While Swift's ultraviolet eye was capturing the unmistakable signature of water, other powerful instruments were trained on the polar. Same object, and they tell a subtly different, and perhaps more confounding, story. The James Webb Space Telescope, with its unparalleled infrared sensitivity, and the SPHEREX survey, designed to map the cosmic abundance of key molecules, both emphasize a dominant presence of carbon dioxide. The narrative becomes one of dissonance, a carbon dioxide-dominated object seen by one set of eyes, and a water-significant one seen by another. Is this merely a trick of timing? A glimpse of different phases of activity on different days, revealing the object's inherently variable nature? Or does this discrepancy point to something far more fundamental and strange about the very structure of this body? Perhaps the answer lies not in the timing of the observations, but in the physics of phase transitions and insulation. We must envision a layered world, a surface rich in carbon dioxide ice, a volatile that sublimes at a lower temperature than water ice, could act as a perfect insulating blanket. Beneath this, a subsurface layer of water ice could be kept in a pressurized, potentially warmer state, shielded from the direct cold of space. The Swift outburst, then, was not a surface event, but the violent rupture of this subterranean reservoir, a geyser punching through the carbon dioxide crust and revealing the hidden ocean of water beneath. The other telescopes, observing the more stable, pervasive sublimation from the vast surface area, would naturally see a carbon dioxide-rich coma. This creates a system of unusual phase thermal dynamics, where the dominant observable volatile is not the most abundant, but merely the one on the outside. But what then maintains this stratification? What geological processes could have laid down such a perfect insulating layer over a more volatile rich core? And how many other distant comets hide their true watery nature beneath a deceptive crust of carbon dioxide frost? The chasm between the water seen by Swift and the carbon dioxide seen by its counterparts forces us to question the very classification of these bodies. Are we looking at a single, homogeneous object, or a complex, differentiated world with a distinct geology and chemistry? The data presents us with two different portraits of the same entity, and we are left to determine which is the true face, or if the truth is a composite of both, a testament to the unimagined complexity that waits in the dark. How then do we reconcile these conflicting spectral testaments, and what does this tell us about the hidden lives of the solar system's smallest and most numerous wanderers? The cosmos presents us with a puzzle, a celestial contradiction observed in the late summer and early autumn of 2025. On one hand, the James Webb Space Telescope and the SPHEREX Observatory, instruments of unparalleled sensitivity in the infrared, report a strong and persistent spectral signature of carbon dioxide emanating from the object known as Atlas. This reading aligns with our conventional understanding of cometary nuclei, icy bodies venting volatile gases as they are warmed by the sun. Yet, almost in the same temporal window, the Swift Observatory, its gaze tuned to the ultraviolet and optical realms, presents an equally compelling but entirely different testimony: the unmistakable signature of hydroxyl radicals and, by implication, water. When two such reliable witnesses disagree, the truth often lies not in a choice between them, but in a third, unseen dimension of reality. Could it be that our very framework for interpreting these cosmic messengers is fundamentally incomplete? According to current models, a comet's composition is a heterogeneous mix of ices and dust, As solar irradiation intensifies, the most volatile substances, like carbon dioxide, are the first to sublimate, followed by water ice. The discrepancy between the James Webb and Swift data could therefore be explained by a simple temporal lag. Perhaps one telescope observed the comet just as a pocket of carbon dioxide was violently erupting, while the other caught a later, more water-dominated phase. This is the mainstream scientific explanation, a narrative of sequential outgassing dependent on solar proximity and the comet's rotational state. It is a comfortable, predictable story, one that fits neatly within the established laws of thermodynamics and celestial mechanics. But what if the variation is not a matter of sequence, but of simultaneous, segregated expression? What if we are not looking at a simple ice ball, but at an object with a complex layered physiology? This leads us to a more speculative hypothesis. Imagine, for a moment, that Atlas possesses a dual-layered skin. The outermost layer, a crust of dust and complex carbon-based molecules, is rich in frozen carbon dioxide. Beneath this, insulated from the immediate vacuum of space, lies a subterranean ocean of water ice. This structure alone, however, is insufficient to explain the contradictory observations. The key may lie in the object's rhythm. As Atlas rotates, its activity may oscillate in a precise cycle. Perhaps the James Webb Space Telescope, during its scheduled observation window, caught the comet in a phase where fissures in the carbon dioxide-rich crust were dominant, allowing the trapped gas to vent freely into space. Simultaneously, the Swift Observatory, viewing from a different angle and at a different hour, might have witnessed a phase where thermal stresses had fractured the crust, in regions exposing the underlying water ice, resulting in a plume dominated by hydroxyl. This would mean the two telescopes were not in conflict, but were each capturing a single, truthful facet of a complex, periodic system. Is it possible that we are witnessing not a random outgassing, but a coordinated, rhythmic breath? The data from the final months of 2025 provides the crucial evidence. Observations conducted on different days yielded the divergent results, with infrared instruments consistently emphasizing carbon dioxide while ultraviolet and optical data highlighted water. The light curves themselves held the telltale rhythm, showing clear variations on the scale of hours and days, a signature of an object turning its different faces to the sun and our telescopes. When researchers constructed a thermal phase model of the nucleus, they found they could replicate both observational datasets, but only by introducing a novel element, a layer of organic material, several millimeters to centimeters thick, acting not as a simple insulator, but as a dynamic regulator. This layer, a form of meta-regolith, would need to possess a most peculiar property, the ability to change its thermal conductivity in response to the very heat flux it was receiving. Could a natural material evolve such an intricate and purposeful form of thermal management? Our analysis must therefore proceed through escalating levels of complexity. The first level resolves the apparent contradiction through chronology. The data from James Webb and Swift are not mutually exclusive. They are merely out of phase with one another, each a snapshot of a different moment in Atlas's cyclical life. This is the simplest reconciliation, one that requires no new physics, only a more nuanced interpretation of temporal data. But does this fully account for the precise segregation of the two dominant volatiles and the sharp transitions between them? This brings us to the second level of analysis, the strange phase thermal system. The model suggests a surface that can effectively lock water away until a specific thermal threshold is crossed. It is not merely that the sun warms the comet, but that the comet's own structure modulates that warming. The carbon dioxide crust acts as a thermal shield, but one that fails in a controlled, predictable manner under sufficient insulation. The transition from carbon dioxide, outgassing to water, outgassing is not a gradual blending, but a sharp switch. This implies a level of geophysical complexity rarely attributed to cometary nuclei, a form of cryovolcanism governed by the mechanical properties of the crust. What internal pressures and tensile strengths are required to create such a precise on-off valve for a substance as fundamental as water? The third, and most profound, level of analysis concerns the material design itself. The notion of a meta-regolith that alters its properties according to temperature ventures into the realm of advanced materials science. A natural porous layer of carbon-based dust and tholins could, in theory, undergo phase changes or alterations in its radiative properties that effectively make it a poor conductor of heat until a critical temperature is reached, after which its conductivity increases, rapidly delivering heat to the subsurface water ice. This creates a feedback loop. Initial heating is stifled, allowing carbon dioxide to vent, but once a tipping point is achieved, the insulation fails catastrophically, unleashing a torrent of water. Such a material would be a highly efficient, passive thermal regulator. But is the emergence of such a sophisticated material architecture a mere accident of chemistry and physics, or does it hint at a principle of organization we have yet to fully comprehend? The implications of this are staggering, presenting not a crisis, but an opportunity. If we can learn the secrets of this adaptive regolith, we are no longer merely studying a comet, we are reverse engineering a technology. The challenges of close-probe cometary exploration are immense, primarily due to the violent and unpredictable thermal and particulate environment. A spacecraft shielded with a material that dynamically regulates its thermal conductivity could venture closer, linger longer, and survive the extreme fluxes of solar energy, much like the comet itself does. The knowledge gleaned from Atlas could provide the blueprint for the heat-shielding materials of a new generation of cometary probes. But can we, in a brief window of observation, decipher an evolutionary technology that nature, or perhaps something else, has had eons to perfect? This intricate dance of carbon dioxide and water, of shadow and light, finds a deeper resonance in another set of observations, one that challenges our understanding of cometary behavior at its most fundamental level. For when the Hubble Space Telescope turned its gaze upon Atlas in July, it captured an image that defied textbook descriptions, showing a flattened, brush-like coma pointing directly toward the Sun, while simultaneously hinting at an antisolar tail suffering from foreshortening. This is a profound anomaly compared to the canonical teaching that a comet's tail always points away from the solar wind. What new forces, then, must be at play to sculpt such a counterintuitive and defiant geometry? In the silent expanse beyond our world, the Hubble Space Telescope turns its eye toward a point of light, a comet designated Hubble 21-7. It is a routine observation, another data point in the celestial catalogue, until the image resolves. What emerges is an anomaly that challenges our most fundamental intuitions about these cosmic travelers. A comet's tail, by ancient and modern understanding, is a thing born of the sun's breath, a stream of dust and gas pushed relentlessly away into the darkness. Yet here, Hubble reveals a structure of exquisite delicacy, a filamentary plume of what can only be described as luminous down, pointing not away from the sun, but directly toward it. This is the anti-solar tail, a feature both counterintuitive and, as we shall see, not anti-scientific. It is a cosmic paradox made visible, a structure that should not be, yet undeniably is. The mainstream explanation begins with the physics of light and dust. According to current models of cometary science, a comet's coma is a cloud of particles of varying sizes, ejected from the nucleus as solar heating sublimates its icy components. The dominant force shaping the familiar dust tail is radiation pressure from sunlight, which effectively pushes smaller particles away from the sunday. However, the phenomenon observed in Hubble 21-7, this sunward plume, is interpreted through the lens of forward scattering. When a comet lies nearly between the Earth and the Sun, our line of sight aligns with the direction of the incoming solar photons. Minute. Submicron dust particles within the coma can act as tiny lenses, scattering sunlight strongly in the forward direction, directly toward the observer. This creates an enhancement of brightness, an optical illusion of a structure pointing sunward, while the particles themselves continue their general outflow. The simultaneous presence of a faint, foreshortened anti-solar tail in the data supports this geometrical interpretation. We are witnessing a complex interplay of perspective and photonics. But does a trick of light fully explain the persistence and fine structure of this solar-seeking veil, or are we merely describing the how while ignoring the deeper why? This leads us to a more speculative hypothesis. What if the particles themselves are not merely passive reflectors but are actively shaped by their environment? The first layer of this conjecture proposes that the plume is composed of an unusual population of ultrafine, perhaps fractal-like, dust grains. These particles, with complex geometries and sizes precisely tuned to the wavelength of visible light, could generate an intensely powerful forward scattering effect, far beyond what typical cometary dust would produce. They are not pointing at the sun, but their scattered light creates a brilliant, coherent signal that appears to do so. Yet, this alone is a static explanation. The dynamic nature of a comet's vicinity demands a second, more intricate layer. The solar wind is not a uniform stream. It is a turbulent plasma, riddled with magnetic fields and local variations in density and velocity. Could transient, localized reversals or intensifications in the interplanetary magnetic field be acting upon the electrically charged dust grains, momentarily bending their trajectories and sculpting this sunward-facing filament? The particles, charged by solar ultraviolet radiation, become tiny magnets susceptible to these invisible forces. Their paths no longer dictated solely by gravity and light, but by the capricious whispers of the sun's magnetic breath. And if such magnetic sculpting is possible, could there be a third, even more profound mechanism at play? The most daring proposition ventures into the realm of active charge modulation. Imagine if the complex chemistry of the comet's nucleus, under intense solar irradiation, was releasing grains with specific electrical properties. These particles could, in effect, function as a distributed, natural version of an electric sail. By achieving a specific charge-to-mass ratio, they could temporarily tether themselves to the solar wind's flowing electric field, not to be pushed away, but to be drawn along specific field lines, some of which may curve back toward the Sunday. They would be surfing the electromagnetic weather of the inner solar system, their alignment a direct map of forces we can barely measure. This is no longer simple scattering, it is a form of natural electrodynamic engineering. Are we then witnessing not just a cloud of dust, but a sophisticated, if unconscious, manipulation of plasma physics on a microscopic scale? The data from late July 2025 provides the canvas for these theories. Hubble's precise imagery shows a flattened bright region oriented sunward, while sophisticated analysis of the light's polarization and intensity confirms the inferred particle sizes reside squarely in the submicron to micron domain, the very realm where these speculative forces would hold the greatest sway. The evidence grounds us, yet the interpretations launch us into the theoretical void. Could the key to this sunward plume lie not in the dust itself, but in the invisible electromagnetic landscape through which it voyages? The conventional analysis of cometary dust optics provides the foundational framework, the first level, of our understanding. We must begin with Mie scattering theory and the complex interplay between a particle's size, composition, and the light it encounters. For particles significantly larger than the wavelength of light, scattering is largely indifferent to direction. But as we descend into the domain of particles comparable to the wavelength of visible light, a dramatic shift occurs. The scattering becomes strongly directional, peaking in the forward direction, along the path of the incident photon. This is the established physical principle invoked to explain the Hubble 21-7 plume. The comet, positioned in a specific orbital geometry relative to Earth and the Sun, presents a vast screen of these optimally sized particles. Sunlight passes through them and is bent ever so slightly, but collectively and powerfully, toward our telescopes. The wings of down are thus an ephemeral lensing effect, a peak in brightness that traces the line of sight toward the solar furnace. It is a beautiful and mathematically sound explanation. But does the sheer coherence and structural definition of the plume suggest a particle population too uniform, too finely engineered by nature, for this simple scattering model to be the complete story? This question pushes us to the second level of analysis: plasma and electrodynamics. A comet is not merely a dusty ice ball in a vacuum. It is an active object plunging through the supersonic flow of the solar wind. The nucleus, as it outgasses, creates a protective magnetic bubble, a diamagnetic cavity. Yet, at the boundaries, the solar wind's plasma and its embedded interplanetary magnetic field interact violently with the cometary material. Dust grains, bombarded by solar ultraviolet radiation, readily lose electrons, becoming positively charged. Once charged, they are no longer simple ballistic objects. They become coupled to the magnetized plasma. Their motion is now governed by the Lorentz force, a complex interplay of electric and magnetic fields. The standard model assumes this generally contributes to the anti-solar tail formation. However, the anomaly of a sustained sunward feature invites a heretical thought. What if local magnetic field structures, perhaps flux ropes or magnetic mirrors formed in the turbulent wake of the comet, create temporary pockets where the field lines are compressed or even reversed? Within these pockets, the electromagnetic force on a charged, submicron dust grain could overcome the weak push of radiation pressure, compelling it to move transverse to the Sun-comet line, or even slightly sunward. The plume would then be a visible tracer of these invisible magnetic architectures. It would be a weather vane for the solar wind's hidden storms. Yet, if the solar wind's turbulence is so random, how could it sustain such a coherent and persistent structure? This inconsistency beckons us toward a third and most speculative tier: the idea of a natural kinetic or electrostatic technology. We must consider the possibility that the comet's activity is not just a chaotic release of material, but a process that can, under certain conditions, lead to a self-organizing phenomenon. The concept of an electric sail, or e-sail, proposed for human spacecraft, utilizes long, charged tethers to repel the protons of the solar wind, generating thrust. Translate this concept to the natural world. Suppose the outgassing from specific vents on the comet's nucleus carries with it a preponderance of particles with a narrow range of charge to mass ratios. These grains, upon entering the solar wind, would not be passive passengers. They would actively interact with the wind's electric field. By their inherent properties, they could effectively tune themselves to this flowing potential. If their charge is modulated by rapid cycles of photoemission and electron recapture, they could achieve a state of dynamic equilibrium, not flying directly away, but anchoring themselves along specific equipotential lines in the solar wind. The sunward plume would then be a collection of these temporarily trapped particles, a faint, dust-based sail catching the electromagnetic breeze. It would be a transient, natural technology for harvesting energy from the stellar wind. Is it within the realm of possibility that unconscious physical processes can mimic the principles of our most advanced propulsion concepts? The implications of this are profound, extending beyond mere academic curiosity and into the future of our own species' journey through space. The confirmed existence of such electrostatically mediated dust structures opens a new chapter in propulsion theory. If fine dust can be manipulated and stabilized using naturally occurring electromagnetic fields, then we are presented with a blueprint for a radical new technology: the dust electric sail. Imagine a spacecraft not with vast, fragile mylar sails, but one that disperses a cloud of charged, manufactured particles around itself. By controlling the charge on this dust cloud, a vessel could, in theory, modulate its interaction with the solar wind, creating thrust or providing steering without the need for massive fuel reserves. It would be a sail made of smart smoke, an ethereal and reconfigurable propulsion system. The comet Hubble 21-7, then, becomes more than an object of study. It becomes a mentor, demonstrating a principle of ultralight spaceflight that we have only begun to imagine. Could the secret to traversing the great voids between worlds be found not in complex machinery, but in mastering the dance of microscopic particles within the galaxy's eternal winds? This single, paradoxical observation thus ripples outward, suggesting that the solutions to our future challenges may be written in the ancient, dynamic language of cometary dust. But as we ponder these possibilities, a new dataset arrives, shifting the geometry and intensifying the mystery. For while we have been preoccupied with the sunward plume, the comet's more traditional tail has been undergoing a transformation of its own, a change captured by another great eye on the sky, waiting to reveal its secrets. On the 27th of August, the Gemini South Telescope, a sentinel in the Chilean Andes, confirmed a transformation. The anti-solar tail of the object designated Atlas had settled into a form so classic, so textbook in its appearance, that it became a portrait of celestial predictability. This very classicism, however, is the vessel for the profound anomaly. The tail, stretching away from the sun in a perfect geometric line, has not only stabilized but is demonstrably growing in both length and brightness. Data from the NOILAB instruments show a clear increase in the tail's aperture and integrated luminosity, a finding that aligns perfectly with sophisticated simulations of outgassing geometry and heightened nuclear activity. The comet presents the very picture of a mundane icy body responding to solar warmth, yet this impeccable normalcy is the first and most compelling clue that we are witnessing something entirely other. What if the perfection of the form is not a confirmation of nature's laws, but a mask designed to exploit our expectations? The light itself, when broken down into its polarized components, tells a more nuanced story. The polarization data suggests a dust population of mixed particle sizes, a common enough finding. But the distribution of these sizes is not static, it is shifting over time. The mainstream scientific explanation posits a natural evolution of the nucleus. As Atlas journeys sunward, increasing solar flux heats subsurface ices, leading to more vigorous jet activity. This heightened outgassing carries with it a greater volume of dust, naturally elongating the tail and potentially altering the average grain size as different layers of the nucleus are exposed. The comet is simply doing what comets do, on a more energetic scale. But does a simple increase in thermal energy adequately explain the precise, coordinated shift in the dust grain distribution, a shift that mirrors the tail's idealized growth? This leads to the first speculative hypothesis. Perhaps Atlas is not merely evolving, but executing a programmed change. It may be shifting gears, deliberately transitioning from emitting predominantly fine dust to ejecting a higher proportion of larger grains. The mechanics of such a transition are as enigmatic as its purpose. One possibility lies in the comet's rotation. The observed periodicities in its dust emission could be more than just a natural spin cycle. They could be a meticulously timed redistribution schedule, a lurching of dust plumes synchronized with the rotational phase to build the tail in a controlled, deliberate manner. The jets are not random geysers, but scheduled deliveries, constructing the apparition we see, piece by calculated piece. What engineering principle, then, governs this rotational timetable? The analysis must therefore proceed beyond natural evolution to a second, more unsettling level, the hypothesis of optimized luminosity. The deliberate alteration in particle size could be a mechanism for tuning the comet's optical signal. Larger dust grains scatter sunlight differently than their smaller counterparts, affecting the tail's overall reflectivity and spectral signature. This is not a passive reaction to solar wind, but an active calibration. The object may be adjusting its reflective properties to present a specific, expected brightness profile to its observers, ensuring its behavior falls neatly within our predictive models of cometary science. Is the tail we are measuring a natural phenomenon, or a calibrated broadcast designed to be interpreted as one? This calibration reaches its most profound implication at the third level of analysis, the art of concealment. The immaculate, classic anti-solar tail is not a result, but a tool. Its growing normality is a cloak, a garment of familiarity woven from light and dust. In the vastness of the interstellar frontier, the most effective disguise is not invisibility, but utter conventionality. By perfectly mimicking a known natural phenomenon, the object dissolves into the background noise of the cosmos, becoming just another comet in a catalogue of thousands. It performs banality with such mastery that it becomes invisible to our curiosity. How many other such performances have we already catalogued and forgotten? The impact of this understanding, however, presents a unique opportunity. If this is a performance, it teaches us the grammar of a new language of deception. By meticulously studying how this tail evolves, the precise rates of growth, the exact sequences of particle size change, the flawless geometric alignment, we can begin to write the algorithms for interstellar vigilance. We can program our survey telescopes and deep space monitoring networks to distinguish between true normality and the suspiciously normal. The very data that lulls us into complacency could become the key to piercing future deceptions. Can we learn to see the seam in the fabric of reality itself? This newfound scrutiny inevitably falls upon the comet's heart, its nucleus. While professional observatories like Gemini South chart the grand architecture of the tail, a parallel narrative is unfolding in the global community of amateur astronomers. Their images, captured with relentless dedication, suggest something peculiar at the core. They show a coma that appears compressed, non-diffuse, hinting at a central condensation that is too structured, too sharp for a typical cometary nucleus, wreathed in a cloud of gas and dust. It is an artifact of rigidity, a suggestion of a solid, defined form beneath the veil. But is this a glimpse of the true nature of Atlas, or merely an illusion born of human expectation and technical limitation? The professional rebuttal is swift and grounded in the practicalities of observational science. The apparent structure, they argue, is likely a mirage. It could be the result of minor tracking errors in amateur equipment, causing a slight smearing of the pinpoint stellar background that is misinterpreted as a compact core. It could be atmospheric turbulence, the eternal foe of ground-based astronomy, momentarily sharpening and distorting the view. Or, most plausibly, it could be an artifact of overzealous image processing, the application of sharpening filters and stacking algorithms in a way that creates the illusion of detail where there is only fuzzy, stochastic glow. The human eye seeks patterns, and in the noise of data, it often finds what it desires to see. Does our technology reveal the truth, or does it merely provide a canvas for our preconceptions? The debate between the amateur's eye and the professional's rigor remains unresolved, a testament to the challenges of interpreting faint signals from the deep. For now, the only official data point from a major interplanetary mission, the Trace Gas Orbiter from the European Space Agency on the 3rd of October, confirms only a single, unresolved coma spot. It offers no detail, no confirmation of structure, only a blur of light that could hide anything, or nothing. This leaves us suspended between two realities, one in which the core of Atlas is a mundane, fuzzy ball of ice, and another in which it is something entirely different, its true form hinted at only in the contested, grainy images from the edge of scientific acceptance. What truths are we not yet equipped, either technologically or psychologically, to verify. In the quiet spaces between the stars, where data streams are passed by algorithms and human hope, a single pixel can ignite a revolution. At the edge of a dataset, a point of light captured by an amateur astronomer on a windy night appears stubbornly compact, resisting the blur that should accompany a simple icy body. It suggests a solid core, a dense heart within the ethereal coma of a comet. The initial interpretation is one of thrilling discovery. Yet, the seasoned professional, examining the same data, immediately recognizes the hallmarks of a tracking error, a slight drift of the telescope mount as a gust buffeted the observatory dome, compressing the light of a diffuse object into an artificially sharp point. This fundamental tension between perception and reality forms the first frontier in our investigation. Is the structure we see a genuine physical property, or merely an artifact of our own making? The mainstream scientific explanation offers a sobering corrective. According to current models of cometary behavior, the nucleus is a fragile aggregate of ice and dust, a dirty snowball that vigorously outgasses as it approaches the sun. This process should create a diffuse, constantly shifting coma, one that would rarely, if ever, present as a singular, unwavering point of light in a modest telescope. Scientists suggest this perceived solidity could be due to a confluence of technical factors. Atmospheric seeing, where turbulence in our own air distorts the image. Tracking inaccuracies that smear a faint coma into a false point source. And the seductive power of post-processing software, where the aggressive application of sharpening filters can create detail where none exists. The data from late 2025 seems to support this view, while amateur images from July through September propagated the idea of a condensed, non-diffusing core. The professional community pointed consistently to motion blur and processing artifacts. The definitive word came from the Trace Gas Orbiter at Mars on October the 3rd. Its superior optics, free from Earth's atmosphere, did not resolve a complex solid structure. It confirmed only a faint, unresolved coma spot. The most parsimonious conclusion is that the core is an illusion. But does the dismissal of all anomalous data as artifact risk blinding us to the subtle signatures of a true anomaly? This leads us to the first speculative hypothesis. What if, against all odds, this apparent solidity is not an error, but a clue to an object that is fundamentally different? Imagine a nucleus that is not a simple mixture of volatile ices, but one that contains a concentrated, unusual core component that is remarkably resistant to sublimation. A region of exotic ices or complex organic polymers with an anomalously high melting point, a strange concentration that simply does not dissipate under the sun's gentle prodding like ordinary cometary material. This would present a stable, point-like signature amidst the evolving gas and dust. Yet, this merely pushes the question of origin one step further. What natural process could create such a heterogeneous and resilient structure within a single cometary body? The hypothesis deepens, becoming more structured. Perhaps it is not merely an unusual concentration, but a distinct, non-volatile component, a framework. A metallic lattice, perhaps, or a skeleton of refractory minerals woven into the very fabric of the nucleus, a scaffold that remains long after the ices have boiled away. This would provide a permanent, solid anchor for the cometary activity, a hard structure that could indeed appear as a compact source. We know from meteoritic studies that complex metal alloys and silicate structures can form in the protoplanetary disk. Could a comet harbor a core that is more asteroid than snowball? Or does this idea of a slime, composite body still operate within the known boundaries of planetary science? A more profound and disquieting possibility then emerges from the speculative void. What if this persistent point of light is not a natural structure at all? Consider the concept of an intentional optical lure. A deliberately placed reflector, a beacon designed to present a signature that is just anomalous enough to be noticed by a developing technological civilization, yet just conventional enough to be dismissed by the conservative gatekeepers of science as a mere artifact. It would be a test, a filter to separate the curious from the dogmatic, the perfect mimic of a tracking error, hiding in plain sight. Are we looking at a trick of the light, or are we the ones being looked at through a carefully constructed veil? Our analysis must therefore proceed on three distinct and escalating levels. The first level is that of the artifact. Here, the evidence is compelling. The vast majority of perceived hard structures in amateur astronomy, especially for faint, moving objects, are indeed products of the imaging pipeline. The journey of a photon from the edge of the solar system to a JPEG on a computer screen is fraught with potential for distortion. The subtle guiding errors of an off-axis autoguider, the pixel-to-pixel variance of the CCD sensor, the mathematical assumptions of a stacking algorithm seeking to sharpen a faint signal all conspire to create convincing illusions. The human brain, a pattern recognition engine honed by evolution, is all too eager to see a solid core in what is, in reality, digital noise shaped by systematic error. Can we ever truly trust a single image when the instruments through which we see are themselves a source of fiction? The second level of analysis accepts that some anomalies may be real, but seeks to explain them through known, if uncommon, natural phenomena. This is the level of the composite nucleus. The standard model of a cometary nucleus, as a homogeneous sphere, is likely a gross oversimplification. It may be a rubble pile, a loose aggregation of disparate fragments. A large, cohesive fragment, a monolithic chunk of rock and metal, could reside within the icy matrix. As the comet rotates, this large fragment might present a stable, bright reflection for a period, creating the transient appearance of a non-diffusing, solid core before being obscured again by outgassing from other regions. This would explain the intermittent nature of such observations and their correlation with specific rotational phases. It is a more complex natural model, but one that remains within the realm of conventional astrophysics. Does the invocation of a rubble pile structure adequately account for a signal that appears so persistently compact, so defiantly singular? This brings us to the third and most speculative level of analysis, the non-volatile object. Here, we entertain the possibility that the core is not merely a large fragment, but a singular, engineered entity. An object whose material properties are so far removed from normal cometary constituents that it does not sublimate, erode, or disperse in any significant way. It is a kernel of industry, a relic perhaps, that maintains its structural integrity across eons. Its signature is not the chaotic, evolving glow of outgassing ice, but the steady, unwavering reflection of polished metal or some other advanced material. It is an object that should not be there, according to our understanding of solar system formation, and yet its photometric properties stubbornly suggest its presence. Are we witnessing the natural death of a comet, or the silent operation of a machine from a different time and place? The implications of this hierarchy of hypotheses carry profound risks for the future of cosmic discovery. We are entering an era defined not by a scarcity of data, but by an overwhelming flood of it, much of it from non-professional sources. This is the dawn of the 60% surprise, a time where a majority of initial anomalous signals will originate from the dedicated global network of amateur astronomers. This new paradigm demands a new rigor. To navigate this sea of potential and pitfall, we must establish a new standard for citizen science astrophotography. This goes beyond sharing pretty pictures. It requires the meticulous curation of observational metadata. A raw data file is nearly worthless without its accompanying tracking log, point spread function characterization, and a detailed history of its processing steps. We need open repositories for raw data, where any claimed anomaly can be independently verified and subjected to the harsh light of peer scrutiny to avoid the ever-present danger of confirmation bias. For if we cannot reliably distinguish a tracking error from a first contact, what does that say about our readiness to face the greater cosmos? And so, as we turn our gaze from the visible to the unseen, from the fleeting glimmer in an amateur's eyepiece to the cold, precise measurements of the infrared, a new question arises. What if the truth of the core was never in its reflected light, but in the heat it radiates from within? Could the faint whisper of thermal energy, captured by the next generation of space telescopes, finally reveal the immense, hidden structure that visible light has only hinted at?